Okay, we continue. Next is the properties of the quantifier. Properties of the quantifier is the arrangement of the quantifier. For example, here we have for all x, for all y is the same combination for all y and for all x. And then if you have for some x, for some y, it's also same as for some y and for some x. Okay, this one is the arrangement. Okay, but if you have a different quantifier, for example, you have for some x for all y is not the same for all y for some x. It's not the same. For example, we have there is a person who loves everyone in the world. Okay, and then everyone in the world is loved by at least one person. It's not the same. If you do in the statement, you can find there is a lot of differences. Okay, please bear in mind. Okay, it's not the same. Okay, and then for another example, for universal quantifier, we have a sentence for all x, px is true if and only if px is true no matter what value from the universe of this call is substituted for x. Okay, for example, we have for all x, okay, x is power of 2 is greater or equal to 0. Okay, the square of any number is not negative. Okay, the square of any number is not negative. And then if you have the commutative law of addition, you can have like this for all x, all y, x plus y equivalent to, okay, this one is commutative law. And then another example, if you use the associative law of addition, okay, also the same. This one you use the commutative law. And then if you have the associative law, okay, for all, okay, and then we can have x plus y, and then we have plus z equal to x plus y. Okay, this one is we call it as associative law. Okay, and then we also can have a nested quantifier. We combine one or more quantifier. For example, everyone likes some kind of food. We can go by for all y, for all x, food x, and likes yx. Okay, and then you can see also there is kind of food that everyone likes. Okay, we have foods and Y likes X. Okay. Okay, and then we have three. Someone likes all kind of food. We use conjunction. Here we use the conjunction. Okay, and then every food has someone who likes it. Okay, so we have food. We have Y like X, whereby X is a food, and for some X, for all X, and for some Y. Okay, and then we have quantifier duality. For example, we have seen here. Not everyone likes McDonald's. You put the negation here. Okay, and then either way is true lah. Okay, either way is true lah. Okay, first is true, second is true lah. Okay, you put the negation here. You put for some, and then you put the negation likes. Okay, this one not everyone likes McDonald's lah. And then secondly, no one likes McDonald's. Okay, you can also have X like McDonald. Okay, and then you put negation. No one likes McDonald. And then if you want to have for all X, okay, whereby X like McDonald, okay, you negate. Okay, you negate the segment. Okay, and then fun with the sentences. You can have the implication, the direct sentence, or you can have the bias implications. Okay, for example here, brothers are sibling. Okay, X brother of Y is implies the X sibling of Y. This one is direct of the sentence, and then you can also have a symmetric. X a sibling of Y, and also Y is sibling of X. Okay, this one is the unit. This one is the type of the sentences. Okay, you can find in the quantifier. Okay, you have implication and by implication. Okay, for the implication meanings that the action or state of being involved in something, you implicate. Okay. Okay, then one mother is one female parents. You can have by implication here. Okay, X is mother of Y. Okay, and then X is female and X parent of Y. And then a first cousin is child of parent siblings. Okay, you can have for all X. Y is first cousin of X. Okay, by conditional of for some P for parents. P is parent of X, and PS is siblings of P, and PS is a parent of Y. Okay, this one is first cousin is child of parent siblings. Okay, this one is one mother is one female parents. Okay, other comments about the quantification. To say everyone likes McDonald's, the following is too broad. If you write down X like McDonald for all X, okay, and then we have Rush example. McDonald likes McDonald. Okay, because McDonald cannot like McDonald. We mean that everyone who is a humans like McDonald's. So we define a person. X is a person. Is likes McDonald. Essentially, the left side of the rule declare the class of the variable x. Constraint like often called a domain constraint. Okay, we call it as the domain constraint because not everybody likes McDonald. And then who likes and who doesn't like must be a human. Okay, must be a human. And then we have equality. Equality, we use the usual infix for the operator. For example, we have John is a father is equal to Henry. Okay, you can say also for all x, x is sibling of y, and x equal to y is and you negate. You negate. Generally, we also allows mathematical operation that we needed or required. For example, for all x, y, x is natural number and y is natural number, and x is equal to y plus 1, implied x must be greater than y. Okay, in terms of parent, we can say that sibling in terms of parents. For all x, y is x is sibling of y, is biconditional of x, y, but you need to negate. And for some m, female, negate male equal to female. And then you end the m parent of x and f parent of x and m parent of y and f parent of y. Okay, this one is sibling in term of parent. You list out the siblings. Okay, and then we have this one is the domain. Domain that have three domains. First, we have kinship domain. Secondly, we have numbers, set, and list. Okay, and then the third one is one post wall. Okay, this one is you simplified the first order logic. We call it as a one post wall. Later we see this one. Okay, to interacting with the first order logic knowledge base. Okay, tell the system assertion that John is a person. Okay, we associating with the knowledge base in the first order logic. Okay, you need to ask the question first before you define the facts and also the rules. Okay. Okay. So far, do you have any question? Okay. Basically, You need to apply the domain, and then tell the system basically about the knowledge based paradigm. Objective is to express the domain knowledge in a rich formal language and be able to use the domain knowledge. Okay, domain knowledge as a knowledge base to solve various problems and tasks that arise in the domain by applying multiple form of inferences. Okay, KB is for knowledge base. The paradigm applies strict separation of concept between information and problem solving. Okay, for that we need to analyze the principle and feasibilities of the knowledge base. Okay, in the context of important of the application and configuration problem. Later we see this one. We need to investigate the problems in the perspective of the knowledge based paradigm. Okay, and then we need to know about the types of the answers. Okay, fact is in the knowledge base is yes, fact is not in the knowledge base, we can prove either yes. If you select the yes, you need to prove it. And then if you select the no, otherwise, okay, you no need to prove lah. And then facts contain variables. Okay, a list of binding for which fact can be proven. Example, we have X Fred, X Mary, and so on. Okay, okay. In knowledge base, also have a free, okay, free and bind variables. Okay, to interacting with first order logic knowledge base, we have one post-wall agent. Okay, it's using first order logic knowledge base and perceive smell and breeze, but no glitter at T5. You need to tell the agent about the time, about the time, and then okay, you need to substitute the binding list by should. This one we have learned last week. Okay. Okay. Given a sentence S and a substitution of a mu values, SS denotes for the result of plugging mu into S. For example, we have S X is taller than Y, and then mu X we substitute Mike and Y for Lori, and then S mu taller, Mike is taller than Lori. So you should ask the knowledge base based on the sentences as that return some uh, or all values of mu such that knowledge base equal to sentences of mu. Okay, we have some knowledge base for one post world. We have some type. The first one we call it as a perception. Secondly, we name it as a reflect, and thirdly, we name it as a reflect with internal state. Okay, do you have any question? Okay, when you want to apply the first order logic, you need to know the one post world. One post world. Okay, for example, for the perception, at current square, there have three perception. Okay, another example, we have smell, breeze, smell, or glitter. Okay, you can call it as a B, either breeze or naked breeze, not breeze. Okay, one first. Okay, secondly, you can define as the smell or not smell. Okay, this one is composed mole. And then you need to state influence, okay, by acting the agent move through a sequence of situations. You need to keep track of change. Okay, either you want to hold and then keep track of changing is very essential. Okay, and then situation calculus is only way to represent the change in the first order logic. Situation change. For example, you want to add situation argument to each non-eternal predicate. Example, now in holding goal now denotes situation. Okay, you're holding the goal. Okay, okay. You cannot observe holding T goal holding T cannot be observed. Now you need to add now. Okay, add some situation. Okay, to be observed lah. Okay, and then you deduce the hidden properties lah. Okay, this one you want to deduce the location. Okay, square breezy near a pit. Okay, and then infer the causes. Okay, infer the causes. Either it complete or not lah. Okay, and then we have definition for breezy predicates. Okay, either the breezy is adjacent. A square must contain a pit. And then if a square is not breezy, no adjacent pit contain a pit. And then combining these two, you can find for all y is breezy is biconditional for the x for the pit for some x and x adjacent by y. Okay, this one is deducing the hidden properties. And then this one I have explained to keep change track of change. We need to hold the situation rather than internally. Lah. And then situation calculus is the only way to represent a change in first order logic. Lah. To add the situation, okay, to add the situation, you need to add a now. Now is basically is current situation. Okay, and then keep track of change situation connected by a result function. Okay, we have A and S and situation that result from doing A in S. We have S, okay, first state, and then we followed by the first state. Okay, this one is by graphically representation to keep the track. And then describing the action by using axiom. Okay, you use the effect to describe the change due to the action, and you describe frame to describe non-changes to the action. Okay, for example here, a frame problem, find an elegant way to handle non-change. First one, you use the representation to avoid the frame axiom. Again, and then secondly, you use the inferences to avoid the repeated uh, copy overs to keep track of this state. Okay, and then for describing the action, we need the qualification problem and then a ramification problem. For the ramification is secondary after the primary problem sequences from the qualification problem. For example, here, what if the goal is slippery and nailed down or dot 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 lah. And then for the real action, what about the dust on the goal, wear and tear on the glove lah. Okay, you ramify the problem lah. Okay, in this one is qualification problem, and then you quantification the problem. Okay, you add the details okay, for the problems. Okay, and then after that, you need to describing the action by using the axiom. Okay, each axiom is about a predicate, not an actor, not an action. Okay, for example, we have P true afterward, an action made P true, or P true and no action made P is false. Okay, and then after that, after describing the action, you need to making a plan by using the initial condition, and then you have to query to ask and then to answer lah. Okay, this one a better way. This one is second alternative way to make a plan to represent a plan as a sequence of action. Okay, for example here we ask the query and then ask the knowledge base. Okay, holding a goal and then we plan and then the solution either you forward the query or you grab the query. And then lastly is you need to have the planning system to do the inferences more efficiently than general purpose reasoner. Okay, this one is one purpose. One purpose you need to clarify the problem, and then by describing the action. First, you need to, de- to describe the action, and then quantify the problem. Okay, either you qualification the problem or you ramification the problems, and then thirdly you need to describe the action by using axiom. Then after that you make a plan. Okay, you need to ask again the query, and then you need to answer, and then after that you choose which plan is work for the axiom. Okay, this one is just for the inferences. Okay, so far, do you have any question? Is it okay? I feel okay, ka? Okay.